Hey guys, welcome back. Today we're going over 9.5 symmetry, and there's going to be just a lot of vocab in this video. I'm going to give you a heads up right now. So if you need to rewind the video a couple times to make sure you heard an explanation, just be prepared. You might have to do that. Now, symmetry. The basic meaning of symmetry is, cut things in half. Things are even on both sides. When a figure has symmetry, that means that there is a rigid motion. Whoops. Okay? And by rigid motion, I mean a reflection, a translation, a rotation, or a glide reflection. There's a motion that the figure goes around. Okay? And it's that going around bit that gives it symmetry. Okay? So think back maybe to algebra when we talked about parabolas. All right, and there was this thing called the axis of symmetry down the middle. All right, and if you folded the parabola along the axis of symmetry, it matched up with each other. If you checked the points matched up. Okay, the y values were the same. Okay, that's having symmetry. Now, this particular type of symmetry is called line symmetry. Go figure, because it's symmetric around a line. Now, the line itself is called the axis of symmetry, like I just said. And what this means, if a figure has line symmetry, it means that when it's reflected, it maps onto itself. So if I flip the parabola, or if I flip this V thing, and I reflect it over that axis, you're going to get the image is going to match up with the pre-image exactly. Okay? So line symmetry reflects over an axis symmetry, and matches exactly. Now, the next vocab word on our list is rotational symmetry. Okay? Now, beforehand, we were reflecting along a line. Okay, well, now we're rotating along kind of like a nail. Okay, so imagine that you have let's go with a smiley face or a button. Okay, and you nail that. Actually, we can call it a pinwheel, even better. Okay, imagine you have a pinwheel. I'm going to draw it down here. Okay, if anybody doesn't know what a pinwheel is, ask me in class. Okay, you've got a pinwheel here. Mine's in the shape of a flower. And when the wind blows, okay, it spins around that nail in the middle. Okay, and every time it spins, it gets to a certain point where it matches exactly. Okay, the petals will all be in the exact same place. You get to a certain point where if you keep spinning, you can't tell if that was the original point or if it spin a couple spins. Okay, that's rotational symmetry. It's rotating around a center point, and the center is called the center of symmetry. Okay, and as you can see here in the image the PowerPoint gives you, we've got a square or a diamond. Okay, and the pre-image starts right here at 0 degrees, and then it rotates. It rotates 45, it rotates 90, it rotates 180, 270, all the way around. Now, due to the fact that it's going in a circle, we really only care about 0 to 360. Okay, because it's a circle. You have 0 degrees, meaning you haven't spun at all, and then you've got 360, which means you've come around an entire circle. Now, in order for there to be rotational symmetry, the figure has to be mapped onto itself by the rotation. So that means when it rotates, the image matches the pre-image exactly. Okay, so in these 5 images we've got down here, there's really only 4 that have rotational symmetry. You have the pre-image, and then if you rotate it 90 degrees, notice how the pre-image and 90 degrees match exactly. And if you rotate it again 180 degrees, well, again, it matches exactly. Okay, it's the exact same image. And if you rotate it again 270, it matches exactly. Okay, 4 instances of the figure rotating and matching the pre-image exactly. Now 45 over here, I'm going to change colors on you. 45 is there almost as a counterexample. Okay, so just because something rotates doesn't mean it's mapped onto itself. Okay, there's specific degrees that the figure has to go to in order to map onto itself. You can't just spin it a little bit and say, there, see, rotational symmetry. No, it's got to be a specific degree. Okay, in this case, for our square, it's 0, 90, 180, and 270. More vocab words, but we're still talking about rotational symmetry. Now, as I just mentioned, you can't just spin it however much you want. You have to spin it by an exact degree in order for it to have rotational symmetry. Well, order of symmetry, ta-da, the order of symmetry is the number of times the figure maps onto itself. Okay? So in this case, the order of symmetry is going to be 4 because we have 1, the pre-image, 2, 90 degrees, 3, 180, 4, 270. Okay, if we rotate 360, if we rotate that last 90 degrees, we're going to be in the exact same position as the pre-image, which is the reason why we're not counting it. Okay, we count the pre-image, or you can count 360, but you don't count both because they're in the exact same position, if that makes sense. So order of symmetry is the number of times the figure maps onto itself as it rotates. Now, the magnitude of symmetry is the angle of rotation. Okay? This is the smallest angle the figure is rotated so that it maps onto itself. Okay, this is what I was talking about in the last slide. The reason why 45 is not included in our order of symmetry is because it doesn't match the pre-image exactly. So I can't just spin my figure however much I want. I can't spin it 20 degrees and say, there, it's rotational symmetry. No, I have to spin it to, at the very least, 90 degrees. 90 degrees is the exact smallest that I can go to for it to match the pre-image exactly. Okay? Now, the relationship between order and magnitude is by the following equation. Okay? So if you didn't know the exact magnitude of a figure, you can use this equation. So you have 360, the full circle, divided by the order. Okay? So 360 degrees, the full circle, divided by the order of symmetry. How many times does the figure map onto itself? In our case, it maps onto itself 4 times. So our thing is going to be, is going to be 360 divided by 4, which ends up being 90. And as you can tell in the next slide, it does. The order is 4, and the magnitude is 90. Now, those were just 2D shapes. Okay, so you have line of symmetry and rotational symmetry. Those are for 2D figures. Now we have 3D figures. Okay, plane symmetry and axis symmetry. And if you can believe it, they're just the 3D versions of the 2D ones. Okay, plane symmetry is if the figure can be mapped onto itself by a reflection in a plane. Okay, so instead of just a line reflecting over another line, you've got now a 3D object reflecting over a plane. Okay, so think about this as basically like a mountain. Okay, here's my mountain. Isn't it beautiful? And there's the water. We got a lake down here. Here's the lake. Okay, plane symmetry would be very similar to the reflection of the mountain in the water. Okay, you have the mountain on top, the lake is the plane, and then the mountain's reflection in the water would be the other side. Okay, there are other examples that are coming up. That's just one to kind of give you a visual. Now next we have axis symmetry, which is, again, instead of spinning a 2D figure around a point, you're now spinning a 3D figure along a line. Okay, think the wheels on your car. Okay, the wheels on your car have axis symmetry because they rotate around the axis of your car. And a top could have axis symmetry. So if you spin a top on the ground, the whole 3D figure is rotating along the axis of symmetry in the middle. Okay, so these are now 3D symmetry. Okay, so here we have an L-shaped prism, and the question is, does it have plane symmetry, axis symmetry, both, or neither? Because 3D figures can't have both. All right, so if you're looking at this L-shaped prism and if you're looking at it coming towards you, okay, so it's kind of coming in this direction, you could be thinking, no, it doesn't have plane symmetry or axis symmetry. But remember, these are 3D figures. And so now think about the figure going this way. Okay, you can kind of see it, or you can actually see it in the picture beneath. That green plane is dividing the L-shaped prism in half. Okay, one half of the prism matches the other half exactly. Okay, so the plane symmetry doesn't always have to be coming towards you. It can be going horizontal to you as well. So keep that in mind. These are 3D figures and you can manipulate them as such. Next, we have a regular pentagonal prism. And this thing actually has both plane symmetry and axis symmetry. Okay, so in this case, you can cut the prism in half going along the middle, as you can see it down there. But you also have this axis of symmetry in the middle. So if you were to stick a straw or a stick through this through this prism and spin it, well, it would spin and it would match exactly every so often on the correct degrees. Okay, axis symmetry and plane symmetry, this figure has both. All right, here we go. So we have 4 figures here, and the question is does it have plane symmetry, axis symmetry, both, or neither? Okay, you're going to ignore any of the markings. We're not paying attention to that. I just want to know if these things have one, the other, both, or neither. So make your decision on 3A. Going to change the slide in 5, 4, 3, 2, 1. The football figure has both. It has both plane symmetry and axis symmetry. And you can almost kind of see it. The axis goes right through the stitching. If any of you have played football before, you can probably see the football spinning in your head. And then if you turned that into a plane of sorts, you could also cut the football in half along that same plane. Okay, so both axis and plane symmetry. All right, the glove. Make your decision in 5, 4, 3, 2, 1. Neither. There is no way you can cut a baseball glove so that both halves are exactly the same. It just won't work. If it is, it's broken. Even then, I don't think it'll work. All right. There's also you can't stick a string or a stick through it and spin it so that it matches. It's neither. All right. The helmet. 5, 4, 3, 2, 1. The helmet has plane symmetry only. All right. And the plane goes right down the middle. So you can have a plane going right down the middle. If you split it down the middle, there it is, plane symmetry. This doesn't really have axis symmetry because if you stuck a stick through the helmet, these side curves, they don't really do it. If you spin it, it's not going to match beyond the 2 points of reflection, and in that case, it's just a plane symmetry. All right, last but not least, the baseball bat. Decide in 5, 4, 3, 2, 1. It is both. And you can probably see it without me drawing it, but I'll try to anyway. The axis is going along the middle here. And then if you took a knife to the bat and cut it, you have plane symmetry down the middle. All right, well, that was our vocab heavy PowerPoint. If you have any questions, please let me know, and I will see you next time.